Welcome to today's session. In this video, we'll dive into the problem find the kth largest integer in the array. This is a popular problem that tests your understanding of sorting, heap-based optimizations, and other creative approaches to handling arrays efficiently. Let's get started. The problem asks us to find the kth largest integer in an array of strings. Here, the array nums contains integers represented as strings, and we are given an integer k which specifies the rank of the largest number we need to retrieve. It's important to note that the integers are stored as strings to avoid issues with integer overflow, especially when the numbers are very large. For example, numbers with hundreds of digits can be easily represented as strings, but they would not fit into standard numeric data types. Additionally, if two integers in the array are equal, their string representations are considered identical. The term kth largest means that the integers need to be sorted in non-increasing order, and we must identify the kth number in that sorted list. The input will consist of the string array nums and an integer k, and the output will be another string representing the kth largest integer. Let's look at some examples to understand the problem better. In the first example, we are given nums equals 3, 6, 7, 10, and k equals 4. To solve this, we sort the integers in non-increasing order, which gives us the sequence 10, 7, 6, 3. Here, the fourth largest integer is 3, so the output is 3. In the second example, nums equals 2, 21, 12, 1, and k equals 3. After sorting the integers in non-increasing order, we get 21, 12, 2, 1. The third largest integer in this sequence is 2, so the output is 2. These examples show how sorting the strings as integers allows us to easily identify the kth largest value. In the third example, we are given nums equals 0, 0, 0, and k equals 2. Here, all the integers in the array are equal to 0. When sorted in non-increasing order, the sequence remains 0, 0, 0. The second largest integer in this case is still 0, so the output is 0. Moving on to the constraints of the problem, the length of the array nums can be as large as 10,000, and each string in the array can be up to 100 characters long. This means we could be dealing with arrays containing very large numbers, and our solution must handle this efficiently. Additionally, each string consists only of digits, ensuring that the input strictly represents integers. Furthermore, each string representation of an integer does not contain leading zeros, except for the special case where the number itself is 0. For example, 0001 is not valid, but 0 is. Some edge cases to consider include scenarios where all the strings are of equal length. In such cases, the comparison between integers would rely on lexicographical order. For instance, in nums equals 123, 456, 789, with k equals 2, we would sort the strings lexicographically to determine the second largest value. Another edge case is when all the strings represent the same number, as in nums equals 0, 0, 0, with k equals 2, where the result will always be the same number. Finally, for large values of k approaching the length of the array, it's essential to ensure that the algorithm efficiently identifies the kth largest integer without performance bottlenecks. To solve the problem of finding the kth largest integer in an array, we first consider the brute force approach. The intuition here is straightforward. Since we're interested in the kth largest element, we can sort the entire array in descending order and directly return the element at the kth position. This guarantees correctness because sorting arranges all elements in the desired order. To implement this, we first convert the nums array from strings to integers, ensuring proper numerical comparison. Then, we sort the array in descending order and return the kth element, where the indexing is 1-based. While simple to implement, this approach is not efficient for large arrays because sorting the entire array takes n log n time, which is unnecessary when we only need a single element. Additionally, the space complexity is n, due to the conversion of strings to integers. So, while this method is easy to understand and implement, it falls short in performance when dealing with larger inputs. Now, a more efficient approach involves using a min heap. The key idea is to dynamically maintain the k largest elements in the array, ensuring that the smallest of these k elements, the root of the heap, is always the kth largest. To implement this, we use a heap data structure, such as Python's Heap, to create a min heap of size k. As we traverse the array, we push elements into the heap one by one. If the heap size exceeds k, we remove the smallest element, which ensures the heap always contains only the largest k elements. Once all elements have been processed, the root of the heap contains the kth largest element. This approach is significantly more efficient than sorting, with a time complexity of n log k, since each insertion into the heap takes log k, and we perform this operation for all n elements. The space complexity is reduced to k, as we only store k elements in the heap. While slightly more complex to implement than the brute force method, this approach is much faster for large arrays, particularly when k is small relative to n. Another viable method is the quick select algorithm, which is a variation of quicksort. This approach avoids the overhead of fully sorting the array by leveraging partitioning around a pivot. The process begins by randomly selecting a pivot and dividing the array into two groups, elements greater than the pivot and elements less than the pivot. Based on the size of these groups, we can determine whether the kth largest element lies in the left partition, the right partition, or if it is the pivot itself. We then recurse on the appropriate partition until we find the answer. This technique is highly efficient on average, achieving n time complexity, though it can degrade to n superscript 2, in the worst case, such as when the pivot is poorly chosen repeatedly. Additionally, quick select operates in place, requiring only 1 extra space. While this method is optimal for large inputs in terms of average case performance, its implementation is significantly more intricate, and it requires careful handling of edge cases, such as arrays with duplicate elements, to ensure correctness. Among the approaches considered, we choose the min-heap strategy as the most balanced solution for this problem. It combines simplicity of implementation with efficient performance, making it suitable for both competitive programming and real-world applications. Unlike the brute force method, the heap approach avoids fully sorting the array, which saves both time and computational resources. At the same time, it is more predictable in performance compared to quick select, which, while theoretically faster on average, can degrade to n superscript 2 in rare scenarios, making it less reliable. Sorting the array is also unnecessary here, as we do not need the entire order of elements, only the kth largest. Sorting n log n time complexity is slower than the min-heap n log k for larger arrays, especially when k is much smaller than n. By offering a clear trade-off between efficiency and implementation simplicity, the min-heap approach stands out as the ideal choice for solving this problem. Here, we're tackling the problem of finding the kth largest integer in an array. To solve this, the brute force approach involves sorting the array and indexing the desired element. First, we need to validate our inputs. If the array is empty, we should return an appropriate error message or value, and the value of k must fall within the valid range of 1 to the length of the array. If k is out of bounds, an error message should also be returned. Once the inputs are validated, we sort the array in descending order. This can be done using built-in sorting functions, such as Python sort, with the reverse equals true parameter, or by implementing a custom sorting algorithm like quicksort or mergesort. Sorting arranges the elements in decreasing order, making it straightforward to locate the kth largest element. Finally, we access the kth largest element by indexing the array at k1, since arrays are zero-based. This simple process gives us the desired result. After sorting and identifying the kth element, the final step is to output the result. For example, if we're given the input array 3, 2, 1, 5, 6, 4, and k equals 2, we begin by validating the inputs. The array is not empty, and k is within the valid range of 1 to the array's length, so we proceed. Next, we sort the array in descending order, resulting in 6, 5, 4, 3, 2, 1. Now, we access the element at index k1, which is 1 in this case, and retrieve the value 5. This value is the second largest element in the array. Returning this value completes the process, giving the correct result. Sorting the array gives us several key insights. First, sorting guarantees accuracy because it arranges all elements in the proper order, allowing us to directly index the kth largest value without ambiguity. Regarding time complexity, sorting the array is the most computationally intensive step, taking n*log n time. Once the array is sorted, accessing the kth element is a simple O1 operation. This leads to an overall time complexity of n*log n. Space complexity depends on the sorting implementation. If we use an in-place sorting method, the additional space required is 1. However, algorithms like merge-sort, which create new subarrays, would require n space. Finally, we must consider edge cases. For instance, with a single element array such as nums equals 1 and k equals 1, the output is 1. In arrays with duplicate values, like nums equals 3, 3, 3, 3, and k equals 2, the output remains 3. If k is invalid, such as nums equals 1, 2, and k equals 3, we should return an error message. Now, let's look at the data structures and operations involved in this approach. The input data is stored in an array, which allows direct indexing of elements. Sorting modifies the array in place when using built-in methods, which helps to minimize memory overhead. The algorithm relies on two main operations, sorting and indexing. Sorting is the backbone of this approach, and efficient algorithms like quicksort, mergesort, or heapsort can be employed to rearrange the elements. Once the array is sorted, indexing is used to directly access the kth element by its position, which ensures quick and accurate retrieval of the result. While the brute force approach is straightforward, it has certain limitations. Its time complexity of n*log n can be suboptimal for very large arrays, especially when k is much smaller than n. In such cases, a more efficient method, like quickselect, can be used to reduce the time complexity to n on average. Quickselect avoids sorting the entire array by partitioning it around a pivot, focusing only on the partition that contains the kth largest element. Another optimization is a heap-based approach. By maintaining a min-heap of size k, we can ensure that the root of the heap is always the kth largest element. This method has a time complexity of n*log k, and is particularly useful for streaming data or large datasets where memory efficiency is critical. Both of these optimizations offer faster and more resource-efficient solutions for finding the kth largest element in an array. This implementation solves the problem of finding the kth largest integer in an array where the numbers are provided as strings. The function kth largest number accepts two inputs, nums, a list of strings representing integers, and k, the index of the largest number we want to retrieve. First, the sort method is used on the nums list. Since the numbers are in string format, we need to convert them to integers for comparison. This is achieved using a custom sorting key equals lambda x, int x. The reverse equals true parameter ensures that the list is sorted in descending order, so the largest numbers come first. After sorting, the kth largest number can simply be accessed via nums, k1, because Python uses zero-based indexing. Finally, the function returns this value as a string, which is required by the problem's constraints. This solution efficiently handles the sorting and retrieval in n-log n time complexity due to the sorting step. It works well within the constraints of the problem, ensuring correctness by directly comparing integer values during sorting and returning the result in the expected format. This is the Java implementation for LeetCode problem number 1985, find the kth largest integer in the array. The logic mirrors the provided Python solution. Key differences include the use of Java's arrays.sort with a custom comparator to sort strings based on their integer values. Java's strong typing and the compareTo method are used to handle lexicographical comparisons when the string lengths are equal. The code is concise and follows Java conventions. To solve this problem, we start with a basic example where the input list is 3, 6, 2, 8, 4, and we need to find the second largest integer. The first step is to sort the list in descending order, but since the elements are strings, we use a sorting key that converts each string to an integer, ensuring correct numerical comparison. After the sorting process, the list becomes 8, 6, 4, 3, 2. Now that the list is sorted, we can directly access the kth largest element. Since k is 2, we look at the element at index k1, which is index 1, giving us the value 6. This is our final output for this example. Now let's consider a slightly more complex example where the input list contains larger integer values as strings, 23, 102, 34, 56, 1010, and k is 3. Just like before, we sort the list in descending order based on their integer values using the same sorting key, int x. This produces the intermediate sorted list, 1010, 102, 56, 34, 23. After sorting, we can directly access the kth largest element. With k equal to 3, we look at index k1, which is index 2, and find the value 56 foot. Thus, the final output for this example is 56 foot. For our last example, we examine an edge case where the input list contains only a single element, 7, and k is 1. Since there is only one element, the sorting step doesn't change the list, and it remains as 7. Here, the task is simply to access the first largest element, which corresponds to index k1, or index 0. The value at this index is 7, making it the final output. A few key observations from these examples include the fact that the sorting step ensures numerical comparison while preserving string formatting. The kth largest element is directly accessed using the k1 index after sorting, and the function consistently returns the result as a string, which aligns with the problem's requirements. The time complexity of this solution can be broken down into two main steps. First, we have the sorting operation. The sort function is applied to the array, using a custom key function that converts strings to integers for comparison. Sorting an array of size n typically requires n log n operations. However, because the key function converts each string to an integer, there is an additional overhead of n asterisk m, where m is the maximum length of a string in the array. When we combine these, the overall time complexity for sorting becomes n log n plus n asterisk m. After sorting, we simply access the kth largest element, which is an O1 operation since retrieving an element from a list is a direct access. Therefore, the total time complexity is dominated by the sorting step, and the final complexity of the solution is n log n plus n asterisk m. Let's now discuss the space complexity of the solution. First, we have the input storage. The list nums is stored in memory, and since each string can have a maximum length of m, the total space required for the input is n asterisk m. Next, there is the overhead of the key function. The custom key function converts each string to an integer during sorting, but Python's sorting algorithm performs comparisons in place and does not create additional arrays. As a result, these conversions do not contribute to the space complexity. Finally, Python's sort function is in place, which means it does not require any extra memory to store the sorted result. Putting these together, the overall space complexity of the solution is determined by the storage of the input list, which leads to a final space complexity of n asterisk m. Now, let's compare this approach to other potential methods. A brute force solution would involve converting all strings to integers, storing them in a new list, sorting that list, and then retrieving the kth largest element. This approach would require additional space for the converted integers, leading to a space complexity of n asterisk m, and the sorting step would still have a time complexity of n log n. The current approach eliminates the need for creating a separate list, reducing space usage. Alternatively, we could optimize further by using a heap-based approach. Instead of sorting the entire array, we could use a heap to find the kth largest element. This would have a time complexity of n asterisk m plus k asterisk m, and a space complexity of k asterisk m. Finally, whether we consider the best, average, or worst case, the time complexity for the current solution remains n log n plus n asterisk m, because sorting is unavoidable and always requires n log n comparisons. The additional n asterisk m term comes from converting strings to integers during comparisons, which is consistent across all cases. When solving this problem, there are a few common mistakes to watch out for. One of the most frequent errors is sorting the array in the incorrect order. For example, if you sort in ascending order instead of descending, you might end up selecting the wrong kth largest element. To fix this, ensure that your sorting explicitly specifies descending order, or adjust the indexing appropriately. Another common issue is off by one errors. Since array indices are typically zero-based, forgetting this can cause you to select the k1 th or k plus 1 th element instead of the kth. A simple fix is to double-check the index calculation after sorting. Finally, relying on brute force solutions, like sorting the entire array for very large inputs, can lead to time limit exceeded errors. For example, if the array size exceeds 10 to the power of 5, sorting becomes inefficient. A more optimal solution is to use a heap, which operates in n log k time, making it better suited for large datasets. Misunderstanding whether k is 0-based or 1-based is another common pitfall. If you assume the wrong convention, your logic might fail. Always confirm whether k starts from 1 or 0 as specified in the problem statement. Another mistake is not handling edge cases. For instance, if k is out of bounds, such as when k is greater than the array size or less than 1, your solution could break. To prevent this, include explicit checks for invalid k values and handle these scenarios gracefully. Now, from an interview perspective, this problem is an excellent example of a selection problem where the goal is to find the kth smallest or largest element. Recognizing this pattern can help you identify optimal approaches, such as using heaps or the quick select algorithm. Keep in mind the trade-offs between different methods. Sorting is simple but inefficient for large inputs, heaps are more memory-intensive but faster for larger datasets, and quick select is the most efficient in the average case but can be tricky to implement correctly. In addition to algorithmic choices, it's important to clarify the constraints of the problem. For example, is the input already sorted? Are duplicates allowed? What should the solution do in edge cases? These are critical questions to confirm, as they can significantly affect your approach. Also, be prepared to discuss the space versus time trade-offs of your solution. For instance, using a heap might be faster, but it requires additional memory, while quick select is an in-place algorithm but can be harder to debug. For further practice, consider exploring related problems. Examples include LeetCode 215, which also involves finding the kth largest element in an array, LeetCode 703 for working with a stream of elements, LeetCode 347 for identifying the top k frequent elements, and LeetCode 378 for finding the kth smallest element in a sorted matrix. These problems build on similar concepts and will strengthen your understanding of selection problems. There are several alternative approaches to solving this problem, each with its own trade-offs. One common method is the heap-based approach. Here, you maintain a min-heap of size k. As you process elements, you add them to the heap, but if the heap size exceeds k, you remove the smallest element. This ensures that only the k largest elements are retained, with the smallest of these being the kth largest. This approach has a time complexity of n log k, and is efficient for large inputs, though it requires additional space for the heap. Another option is the quick select algorithm. This method involves partitioning the array around a pivot and recursively narrowing down to one side of the partition. Quick select has an average case time complexity of n, making it very efficient, but its worst case runtime is n squared, and it can be harder to implement. Finally, sorting the array and directly accessing the kth element is the simplest approach. However, with a time complexity of n log n, it's less efficient for large datasets compared to the other methods. For related problems, there's also the binary search approach, which is particularly useful for problems like finding the kth smallest element in a sorted matrix. In this method, you use binary search over the range of possible values rather than the actual elements. The key idea is to count how many elements in the matrix are less than or equal to a given value and adjust the search range based on this count. This approach has a time complexity of n log maxmin, where n is the size of the matrix, and it is highly efficient for problems with sorted input. However, it requires the input to already be sorted and may involve additional setup for the binary search logic. This method highlights how leveraging problem-specific properties, such as pre-sorted data, can lead to alternative and efficient solutions. Great job! You've reached the end of this session. We covered the problem, explored multiple approaches, and discussed their trade-offs. Remember, practice makes perfect when mastering these concepts. Don't forget to like, share, and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!